There's another chi-square test we can perform. It's called the chi-square test of association or the chi-square test for independence. When we have two variables and we want to determine whether they're independent of each other, we can use this test. We put the two variables into a table called a contingency table. One variable is the rows, the other is the columns. And what we're going to do is use the totals to calculate the expected values for the table under the null hypothesis that the variables are independent. Then we'll make a chi-square statistic from the observed and expected counts. Here, I've got a table of students' drug use versus parents' drug use. I got this data from the Open Intro package in R. And I don't know if the parents' drug use refers to both parents or at least one or what, but the idea is we want to see if the student's drug use is associated with the parent's drug use. We'll assume that there is no relationship and look for statistical evidence to dispute that. The chi-square statistic is just like the one for the goodness of fit test. It's a measure of the distance between what you observed and what you expected. If this statistic is greater than we'd expect to see by chance, we reject the null hypothesis in favor of the alternative. This statistic follows a chi-square distribution where the degrees of freedom are the number of rows minus 1 times the number of columns minus 1. And I'm referring to just the data, not the total rows and total columns. So this would be a 2 by 2 table. The degrees of freedom are 2 minus 1 times 2 minus 1, which is 1. Our assumptions are independence. Each observation is independent of the others, and observations between groups are independent of each other as well. We wouldn't perform this test on two paired variables. And as with the other chi-square test, we want the expected count for each cell to be at least 5. To get the expected counts for each cell, multiply the row total times the column total and divide by the overall total. You can see that the observed and expected tables have the same totals. The expected number in the first row, first column is the first row total times the first column total divided by the overall total. For row 1, column 2, it's first row total times second column total divided by the overall total. Here's row 2, column 1. And finally, row 2, column 2. For a bigger table, there will be a lot of these cells to calculate. That's why it's better to let R do all the work. Once we have the expected table, we take the observed minus the expected squared divided by the expected and sum them all up. And this gives us a statistic that follows a chi-square distribution whose degrees of freedom are the number of rows minus 1 times the number of columns minus 1. In this case, the chi-square statistic comes out to be 16.91, and this follows a chi-square distribution with 1 degree of freedom. Like the goodness of fit test, this test of association is always a one-sided test. We look for the area ahead of the statistic on a chi-square curve to compute the p-value. We find this in R with 1 minus p-chisk or p-chisk with lower tail equals false. In this case, the p-value is 0.000039, which is very small. At the 5% significance level, we reject the null hypothesis and conclude that there is an association between parents' drug use and students' drug use. These two variables are not independent of each other. We can get the same result using R's chisk test command. There are a couple of ways to do this. If your data is set up the way they have it in the package, where it's two categorical variables, you can have one variable be X and one Y. Or you can just feed it your counts as a table or matrix. With a 2x2 table, it will do a continuity correction by default. I won't get into what that's about here, but to replicate the result I got by hand, I have to set correct to false.